Hello everyone, welcome to Calculus Lecture 8. And today we're going to be talking about Riemann sums. So when we compute a definite integral, last time we talked about the fundamental theorem of calculus, which gives us an exact answer. But today what we're going to be doing is approximating an integral. And so the way we do that is by adding up the areas of rectangles that approximate a curve. So let's say I'm given some curve. Something like this. And I want the integral from this point A to this point B. So it's like the integral from A to B of f of x dx. Now, one way I can approximate this area is by drawing some number of rectangles that are reasonably close to the function and adding up these areas. So in general, there are a couple of different types of sums we have. So one thing we can do is take a left Riemann sum. So this means every rectangle we have, we're always going to have the height be the value of the function on the left. So this looks like this. We can also similarly have a right Riemann sum. So for example, I'm going to draw a similar curve, and now we're going to have our rectangles be a bit taller because they're going to meet the function on the right. Something like this. Now, we can also have what's called a midpoint sum. And these are really annoying because finding out the values takes quite a bit of work. So if you do have to do this, it'll be a very small number of rectangles. But a midpoint sum is basically we just take the value in the middle of the rectangle. So your rectangle is going to meet the function in the middle. So this is usually going to give you a better approximation than a left or a right sum, especially if your function's strictly increasing or decreasing. So that's just something to be aware of. And then you could also have what's called a lower or an upper sum. And so in that case, you don't fix the left or the right, but instead you just pick the lower or the higher value. So in that case, if we have a function that looks like this, well, to make a rectangle here, this value here is lower, and so we're going to have that be the height of the rectangle. Something like this. And then we could also do an upper sum, and in that case, we're going to go with the upper value. And so this is higher, and that's going to be the height of our rectangle. So today we'll be practicing some of these calculations. It's pretty common to see these on the AP exam. On my exam, I had one of these, and it also asked me to figure out whether the sum would be a lower or upper approximation, greater than or less than the actual integral. And you can do this by looking at the derivative, whether it's increasing or decreasing, and sometimes at the second derivative. So let's do a reasonably simple example. So let's say we have a linear graph. And this is going to just be the graph of the function y equals x. Let's say this point is 2. And we want to find or approximate the integral from 0 to 2 of f of x. And y equals f of x over here. So how are we going to do this? Let's say the question tells us to use 4 rectangles and a left sum. So the first thing we want to figure out is what is the width of this rectangle. So we want it to be split into 4 parts. So we know that the total length here is 2. So each individual thing, that's going to be 2 over 4, or 1/2. So this point here is 1/2. 1, 3/2, and finally 2. And now we're doing this left sum, so we're going to have, this one actually has 0 height because it hits the origin. Then we're going to have this, and finally this. So we can see from the graph that the sum of the areas of the rectangles is actually going to be a little bit small. It's going to be an under approximation for the actual integral. And so let's compute this. So the first rectangle is 0. Now the second rectangle, the width of each rectangle, remember, is just 1/2. And then the height, well, the height of the first one is 0. The second one, the height is this point. So f of 1, which is, sorry, f of 1/2, which is 1/2. And f of 1, which is 1. And finally f of 3/2, which is 3/2. So the areas of the rectangles, the first one is going to be 0 times 1/2 plus 1/2 times 1/2 plus 1 times 1/2 plus 3/2 times 1/2. And then we can add these up, so that's 0 plus 1/4 plus 1/2 plus 3/4. And I think that gives a final answer of 1.5. Now we could also do the same thing using a right sum. So in that case, we'll have the same graph. Let this be 2. And so we're finding the area of this. And so again, we're going to split this into 4 parts. But now the heights of our rectangles are going to be on the right side. All right, and then the widths are still going to be 1/2 each. And well, what are these heights? So the first height is this point. So that's f of 1/2, which is going to be 1/2. Then the second one, the height is this point. So that's f of 1, which is 1. The next one's this point. So that's going to be 3/2. And the last one's going to be 2. And so now we add up the areas of those rectangles. Again, the widths are all 1/2, and these are the heights. So we have 1/2 times 1/2 plus 1 times 1/2 plus 3/2 times 1/2 plus 2 times 1/2. So let's add those up. So that's 1/4 plus 1/2 plus 3/4 plus 1. And if I'm doing this right, that's going to give a final answer of 2.5. So you can see that the left sum was 1.5 and the right sum is 2.5. So it's expected that the left sum is lower. And in this case, it'll turn out that the actual area is 2. And that's because it's just a triangle. Right, so this is a triangle, and the base and the height are both 2. So the area, the actual integral, that's going to be 2 times 2 over 2, just base times height over 2, which is 2. So that fell between the left sum and the right sum. which is not surprising because with an increasing function, the left sum will always be a lower approximation and the right sum will be an upper approximation. If the function is decreasing, that switches. The left sum will be an upper approximation and the right sum will be a lower approximation. We can also try and do a midpoint sum. So let's try doing that. And I'll just do the same example so you can see how this works. So we again have our line, y equals x, say this is 2. I'm drawing this a bit bigger because this will be a bit harder to draw. Now the midpoints, so we have our 1/2s, which are the widths of the rectangle, and then we're going to go at the halfway point. So that's this point, this point, this point, and this point. And then we're going to draw our rectangles like that. My drawing isn't perfect, but you can sort of make out where these are supposed to be. And now let's find the areas. So we need to first label this. This is 0, 1/2, 1, 3/2. And then we also need the midpoints now. So we're going to need to do 1/4, 3/4, 5/4, and 7/4. And now these are the heights of the rectangles. The function value is just y equals x. So these are in fact just going to be the heights. So now the widths of the rectangles are again 1/2. So now we're going to have 1/2 times 1/4 plus 1/2 times 3/4 plus 1/2 times 5/4 plus 1/2 times 7/4. And let's add those up. So that's going to be 1/8 plus 3/8 plus 5/8 plus 7/8. So 1 plus 3 is 4, plus 5 is 9, plus 7 is 16 over 8, which is 2. And so we see that the midpoint sum gave us the exact answer. And in general, that won't happen. It only happened in this case because it's a line. But the midpoint sum is something we actually expect to be closer to the answer than the left or the right sum. So let's do another example. All right, find the area under the curve. For the graph y equals x squared. On the interval from 1 to 5, using a left sum of 4 rectangles. So that's a lot of information, but see if you can solve it. I'll pause for a moment and then give the answer in a few minutes. All right, so let's do this. So just to have an idea of what it looks like. It's not really perfect, but all right, so there's our graph. Say this is 0, this is 5. This point would be like 5,25, definitely not to scale. And we're looking on the interval from 1 to 5. And then we're going to take a left sum of 4 rectangles. So this is going to look something like this. All right, so first thing first, what are the widths of these 4 rectangles? So that's just going to be 1, we can see from here. Now we need to find the heights. So the first rectangle, the height here is f of 1. All right, because the height's given by this point. And so f of 1 is 1 squared, which is 1. So the height of the first rectangle is 1. Now the second rectangle, the height's going to be this point. So that's f of 2. So that's 2 squared, which is 4. All right, the next one, the height of this third rectangle is this point, the y coordinate of this point, which is f of 3, and that's 9. And finally, the height of the last rectangle is this one. So the height is f of 4, which is 16. And now we can just add these up. So that's 1 times 1 plus 1 times 4 plus 1 times 9 plus 1 times 16. So 1 plus 4 plus 9 plus 16. So that's 5 plus 9 is 14 plus 16 is 30. So this gives us a left sum of 30. Let's sanity check this. Let's solve the integral using the fundamental theorem of calculus. And let's see, we expect this left sum to be lower, we can see from the graph, so let's double check. So the integral from 1 to 5 of x squared dx, well, what's the antiderivative of x squared? Using the power rule, that's x cubed over 3. And then we're going to go from 1 to 5. So the fundamental theorem of calculus tells us the answer is going to be 5 cubed over 3 minus 1 cubed over 3. So that is 125 over 3 minus 1 over 3. So 124 over 3, which is a little bit over 40. I think that's 41.3. So we can see it's bigger, and this is in fact exactly what we expect. If you want a challenge, you can try and do the same thing with 4 rectangles in the left sum or a midpoint sum. All right, let's do a couple more examples. Here's one more. So again, we're gonna find or estimate the area under a curve. Of the function y equals x cubed on the interval from 0 to 2. Using a right sum of 4 rectangles. So again, I'll pause for a few minutes, so see if you can work this out on your own. All right, so let's discuss it. So let me just draw the graph real quick, or at least a rough sketch. So we have our graph of y equals x cubed, which goes up pretty fast. And this is going to be the point 2, and this is 0. And we're going to be splitting into 4 rectangles. So these are going to be in intervals of 1/2. And we're looking at a right sum. So in this case, we're going to expect our sum to be slightly higher. So just as a sanity check, let's first work out what the answer should be. And then we'll do the Riemann sum. So the integral from 0 to 2 of x cubed dx, well, this is going to be x to the 4th over 4 from 0 to 2, which is 2 to the 4th over 4, which is 4. So this is what the actual area is. Now, let's see if we can find the Riemann sum from the right. So since this is from the right, we expect it to be slightly bigger. All right, so let's do this. We're going to have our 4 rectangles. Okay, and each one has width 1/2. And let's find the height. So the first height is going to be the y value of this point. So that's f of 1/2, which is 1/2 cubed, which is 1/8. Then the second one is the y value of this point. So that's f of 1, which is 1 cubed, which is 1. The next one's going to be this point, so f of 3/2, so 3/2 cubed, which is 27/4. And finally, we're going to have this one, so f of 2, which is 8. 2 cubed is 8. And then we're going to add up the areas of all these rectangles. So it's going to be 1/2 times 1/8 plus 1/2 times 1 plus 1/2 times 27 over 4 plus 1/2 times 8. So what is that? So that's going to be 1/16 plus 1/2 plus 29/4 plus 4. So let's see what that is approximately. The 29/4 is going to be 7 1/4. So this is going to be slightly over 11. In fact, maybe even closer to 12. So we can see that the right sum was quite a bit bigger. Oh, actually, you know what? This is not quite right. This should be a 29 over 27 over 8. I don't know why I added those. So let me fix that. All right, 27 over 8. Let's see if that makes a little bit more sense. So now this is just over 3. So it's like 3 3/8. So the answer finally is going to be close to 8 once we add all of these. So that's still quite a bit more. And we do expect that because as we can see, like these rectangles are quite a bit bigger because x cubed increases very fast. And again, if you want some extra practice, you can try a midpoint or a left sum of this. Let's do one more example. All right, so again, we're going to be finding the area under a curve. Of the graph of y equals 2x plus 3. All right, on the interval from 0 to 6. using the midpoint sum of 6 rectangles. So I'll pause for a few minutes, see if we can work that out. In this case, the function is linear, and we're using a midpoint sum. So we actually do expect the function, the Riemann sum to be exactly equal to the value of the integral. That only works because it's a line, but what happens is that when you have a linear function, let me just draw it. And then we have some rectangle where the middle of the rectangle is where it intersects the graph. Then this excess isn't being counted, but this is actually part of the integral and is so this is basically excess in the Riemann sum, and this is what should be counted but isn't, and they're actually the same. And that's why the Riemann sum should equal the actual integral. So you can actually compute the actual integral and verify that it's the same. So I'll just pause for a few minutes and then go over the answer. All right, so let's go over the answer. So this one's going to be pretty long. So we're splitting this into 6 rectangles. So we're just going into intervals of 1. But it's a midpoint sum. So even though we know the widths are 1, we still need to figure out these heights. I'm not going to draw out all the rectangles fully, but just the heights. So the heights are just going to be what happens when we apply the function to 1/2 and then 1.5 and then 2.5 and so on. So let's do that. So at each of these values, basically, so 1/2, 3/2, 5/2, 7/2, 9/2, and 11/2. And we're going to go over the value of 2x plus 3 on all of these, because that's going to be the height of our rectangle. So 2x plus 3 when x is 1/2. So that's 1 plus 3, which is 4. Then when x is 3/2, we're going to get 3 plus 3, which is 6. And we actually know the slope is 2, so we're just going to keep counting by 2s. The next one is going to be 8, and then 10, and then 12, and then 14. So now we can add those up, and we just have to add up all these numbers because these are the heights of the rectangles, and the widths are all 1, so they don't actually do anything. So we're going to be left with 4 plus 6 plus 8 plus 10 plus 12 plus 14. So we can add those up. So that's 10, 18, 28, 40, and 54. So now let's check if this is actually what we wanted to get. So there are two ways to check this. In this case, because it's linear, we can also just find the area directly. So let's do it both ways. The first way is the fundamental theorem of calculus. So the integral from 0 to 6 of 2x plus 3 dx. Well, what is this? This is going to be equal to the antiderivative of 2x is x squared. The antiderivative of 3 is 3x. And we're going to go from 0 to 6. And at 0, it's not going to do anything, so we're just going to be plugging 6 into this. That's 6 squared plus 3 times 6. So 36 plus 18, and that is 54, which is great. That is exactly what we expected. We could also just find the area directly, because we have a triangle and a rectangle. And we could add these up. We would get that the area of the triangle is 18, and the area of the rectangle is 18. The area of the triangle is 36, and we would get the same overall area. So that's a couple different ways you can do it. Now, I think that's it for today. And next time, we'll be talking about the chain rule. So just as a quick refresher, the chain rule says that if we have two functions, f and g, then the derivative of the composition, so f of g prime of x, that's going to be equal to f prime of g of x times g prime of x. So we're taking the derivative of f and then evaluating at g of x. And then we're multiplying that by the derivative of g at x. We also had another formulation of this that which we used in the context of u substitution, which was that dy dx equals dy du times du dx. And so, for example, let's say we want to find the derivative of e to the 7x plus 1. So let's do it both ways real quick, just as an example. So the first way, when you want two functions and we want to write this as their composition. So it seems to me that a good idea would be f of x equals e to the x, and g of x equals 7x plus 1. So when we compose, and remember when we compose, we always go right to left, so we do g first, then f. So we're going to take 7x plus 1 and then take e to that power. So this over here, that's e to the 7x plus 1, that's equal to f of g. And then the derivative is f prime of g of x times g prime of x. So the derivative of f is just e to the x, but then we evaluate at g of x. So that's e to the 7x plus 1
times g prime of x, the derivative of this, which is 7. So that just gives a final answer of 7e to the 7x plus 1. We could also do it the other way, so we could set u to be equal to 7x plus 1, and then we're trying to find dy dx. So remember that now y equals e to the u. Then we would have dy dx equals dy du times du dx. So what is dy du? That's the derivative of this, so that's e to the u, times dy dx, which is 7. But now remember that we can substitute the u in, and the u is 7x plus 1. So that's e to the 7x plus 1 times 7. So we got the exact same answer, and it was pretty much the same process. So these are just two different formulations of the chain rule, and they're in fact exactly the same. And we'll talk more about this next time and do quite a bit of practice. All right, that's it for today.